Welcome back, National 5, to yet another installment to Mr. Boole's Physics, and this time we're continuing our chat on properties of matter. As you can see, it is cup of tea time in the Boole family household, and today I'm going to talk to you about volume and temperature, and specifically how if we keep pressure constant, what happens to the volume of water when we increase the temperature. So that's what I'm going to try and show you in experiment form this morning. Okay, so let's jump to the cooker and I'm going to try and heat up some water and show you what happens when we increase the temperature. Let's go. Alright, so here we are. We've got our jug and we're going to be measuring in fluid ounces up to the 6 point, and we're going to put our water in to measure the volume, and then we're going to heat it up and see how much it changes. So that is just roughly below the 6. We'll see what happens when we heat that water up. So let's get on with that now. Alright, let's see if this worked. I'm not entirely sure if it did, but let's see if it works a tiny bit. Okay, so looking at this, yeah, do you know what? It's maybe just ever so slightly risen to 6. It might just be the same, but we have been transferring from pot to jug, so we might have lost some water there, but we can see that the volume has maybe increased ever so slightly. We probably need to do this for litres and litres of water for it to be a good result. But we can see that the volume has increased because the temperature has increased. Okay, and if pressure is kept constant, when you increase temperature, you're going to have to increase the volume because the particles are getting faster and therefore hitting off the sides more and therefore expanding in the volume. So we're going to talk more about this in the lesson, and hopefully it makes a little bit more sense once you see the equation and the kinetic theory. Alright, so I'm going to bring my cup of tea over and replace that because it's time to get to work and see what the day has to offer. Alright, National 5, I'll see you soon. Welcome back, National 5, to another installment of Properties of Matter. In fact, the last installment of Properties of Matter. So remember to like, share and subscribe to the videos. But today we're talking about properties of matter, and more specifically gas laws part 2. This is the last section of this topic, and then you are done at your National 5 Physics course. Next week we will be going over this all again as revision, the whole thing. But today we're going to finish off with gas laws part 2 and just get a few of the equations that we didn't get to last time. Okay, so we're going to learn the equations that apply when the temperature, pressure and volume of gases are changing, and then use kinetic theory to explain those gas laws. Now, remember, everything from now on is in Kelvin. You should have done that for last week's questions. It is the same for this week's questions. And as I said before, to get to Kelvin temperature, you need to use the Celsius plus 273. You must make sure you use Kelvin. The same applies for this week. Now, what we're going to look at today is the volume temperature law, or what we call Charles's law. Okay? Now, this is an example of Charles's law. We've seen this before. The particles are in red, and when you have something at like 20 degrees, or I guess 293 Kelvin, they have a certain speed. Okay? So when they have a speed, they will obviously hit off the sides. And when they hit off the sides, they'll be exerting some sort of force, which will therefore create some sort of pressure. Now, when you increase that temperature, looking at this here, you actually increase the speed of the particles. Now, if you increase the speed of the particles, they're going to hit off the sides faster, with more energy, with more force, which creates more pressure. Okay? But in this example, the pressure is being kept constant. Okay, so the pressure is not changing. So if the pressure doesn't change, what does change when the particles are now moving faster because they've got a higher temperature? Well, the thing that is changing is the volume. Okay, so as we see up here, the volume was pushed in. But as you increase the temperature to keep pressure constant, the syringe gets bigger, okay, or the volume gets bigger. Constant mass, constant pressure, which means that when you increase the temperature, the volume must also increase, okay? So as the temperature increases, the speed of the particles increases, giving more collisions with the container walls each second with more force. To maintain constant pressure, I can't repeat that enough, constant pressure, the volume must increase, okay? Very straightforward when we think like that. So a good example of that is like a hot air balloon. Okay, that's why if you had the hot air balloon and they have the heat, that heat is to keep the volume big. Okay, if you have big volume, then you're pressing out that hot air balloon, and therefore you can keep the hot air balloon up. Okay, now example of this, very, very quick example. Remember, I've said there's lots of experiments that might be asked in your prelim on the gas laws. They are not tricky. We've not obviously not doing them in class, but they're very, very, very easy to understand. So for example, in this one, you'd be applying some heat onto the water, and the water will be heating up, and therefore the volume of the tube, or the inside the tube here, like it looks like a thermometer, not the one on the left, the one on the right, you'll begin to see the volume going up because it's getting hotter. Okay? When it's less cold, or when it's more cold, sorry, the volume will decrease. So volume decreases when you have cold, and when you have hot, the volume increases. Okay? So that's just a very simple diagram showing that. Now, we saw that similar example to this last time, and when we use degrees Celsius, we get a very odd looking graph. Now that's because it should extend back to minus 273 degrees Celsius, because at that temperature it's 0 Kelvin. However, if we can just put the volume and temperature scale in Kelvin, we get a perfect graph that starts from 0 and it's directly proportional. Okay? So make sure you memorize these graphs because they're very important. So, wow, that looks shocking. Okay, it's not like that in a PowerPoint when you open that up, but you should be able to see that V1 is divided by T1, not whatever that is. V1 divided by T1 equals V2 divided by T2. So V1 over T1 equals V2 over T2, and temperature must be in Kelvin. So what's the kinetic theory behind this? So obviously we've talked about the previous equations, but what's the kinetic theory about this? As the temperature increases, the speed of the particles increases, giving more collisions with the container walls each second with more force. But we're maintaining constant pressure, so therefore the volume must increase. So remember, the kinetic theory is very important for each of these equations. Now, combined gas equation, this is what you'll actually see in your booklet, okay, or in your equation booklet, which looks like PV over T equals constant. Now, you know the three equations that we have just talked about. Okay, I'm going to do a quick recap of them in a second or two. But this is what's going to be coming up in your equation sheet. So I would suggest writing in the three equations that we have just talked about, because those are the ones you're most likely to do. Okay, so please make sure you do that. Please make sure you do that. The only thing that's a slight difference that is good about this equation is that sometimes you'll get given 5 things, okay? You'll be given a pressure, volume, and temperature, and then you'll be given maybe a pressure and volume, and you'll be asked to find out the temperature. All right? So then you will have to use this equation, and it'll look something like P1 V1 over T1 equals P2 V2 over T2. And some of your questions today are going to be asking exactly that. So let's look at an example. A gas cylinder contains 3 times 10 to the negative 3 meters cubed of gas at a temperature of 230 degrees Celsius. We're going to be changing that to Kelvin. What would the volume be if it was moved to a refrigerator at temperature 0 degrees Celsius? Okay, so I've done the example here. V1 over T1 equals V2 over T2. Now can I just express, when you have the 5 elements, that will become P1 V1 over T1 equals P2 V2 over T2. Okay, so just make sure that you remember that if there's 5 things, you're adding the extra P in there. Okay, and therefore be a massive equation. So V1 over T1, put the values in, equals V2 over T2. Making sure that 503 and 273 are the answers in Kelvin. And then we obviously rearrange it, and we get something like 1.63 times 10 to the negative 3 meters cubed. So if you want to go through that, you can. Okay, just take some time and look at the answer that I did there. Okay, if you paused it before you looked at this, then you're an amazing human being. Well done for doing that. Right. So as I have said before, this is an example of what one of the questions will be in the homework. I am not doing it because I want you to try it yourself in the problems or in the assignment. So this one, for example, says a gas cylinder contains 12 times 10 to the negative 3 meters cubed of gas at a temperature of 5 degrees Celsius. It has a pressure of 4.8 times 10 to the 5 pascals. What would the volume be if it was moved to a heater at temperature 500 degrees Celsius and at a pressure of 12 times 10 to the 5 pascals? So can you see that there's 5 things here? So how are we going to answer this? Well, what we're going to do is we're going to do P1 V1 over T1 equals P2 V2 over T2. Alright, so P1 V1 over T1 equals P2 V2 over T2. So very similar to these equations, except as I've said before, it's just P1 V1 over T1 equals P2 V2 over T2. Hopefully that makes sense. There's 3 questions on that in the assignment, and it's just testing your knowledge to see if you can actually work that out yourself. Okay? So try that yourself. Now, recap. So let's look at a quick recap of everything we've learned. Okay? Remember, the questions are only on the stuff we've just talked about. This stuff is just a recap. Boyle's law. P1 V1 equals P2 V2. Okay? The graphs look like this on the left-hand side, making sure that P is over 1 over V. And then making sure that we understand the kinetic theory at the bottom. Okay, so pause the video, look at this, remember how it all goes, and then we'll move on. Okay, these are important notes, very important notes. Okay, next one, the Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So can you see how each one of these is slightly different? Remember, all these equations are slightly different. All I'm saying for that last example is you're adding for this one here would be P1 V1 over T1 equals P2 V2 over T2. And you'd have 5 things and 1 missing. This one here, remember, just like the last one we saw in Charles's law, we need to have the pressure in the Kelvin scale for it to start from 0. Remember also the kinetic theory, which you can read there. So pause it, look at it, and then we'll move on. Okay, next one. Charles's law, just as we talked about, V1 over T1 equals V2 over T2. The graphs are the same as just above, and we've talked about the kinetic theory there. So things you must know. The graphs, the equations that I would ask you to write down into your equation sheet now, and also the kinetic theory for each. Okay? Those are the 3 important things you must know for each one of these laws. And then we're going to do lots of revision on that next week with past paper questions. Okay? So that's all for this week. Try those questions. If you've got any queries, make sure to ask a question with your teacher and they will be able to help you out. I hope that makes sense, and I hope this stuff is not too challenging for you guys and it goes well. So very well done, National 5, and keep up the great work. Look at this top quality snack for the morning. Let's get stuck into it.